Okay, we're going to get started. First of all, welcome everyone. I'd like to acknowledge that we are the traditional custodians across all the lands on which we live and work, and pay our respects to elders past, present and emerging, and also recognise that the lands and waters that we are meeting on have always been places of teaching, research and learning. It's very, very important. Also, today's International Women's Day. I'd like to recognise the impact and contributions of all the females across research and industry that we work with, and particular the very talented group of females that we are privileged to work with at HILT CRC. This year's theme is Embrace Equity, meaning that we enthusiastically accept, adopt and espouse. And I hope that's a message that each and every one of us take away from today as we celebrate International Women's Day. So welcome to the first public HILT CRC webinar. Many of our partners have been attending our internal webinars over the last year or so. But we thought this topic was of very broad interest, and judging by the registrations we've received, that is certainly the case. And so we've decided to make this a public webinar. Thank you to all those from outside our partnership that are attending, and we'll continue to seek these topics as we continue our mission. So HILT, of course, is driven by the need to de-risk the decarbonisation pathways for heavy industry and ensure that it can prosper through the low carbon transition, utilising the research that the CRC does. Within the partnership, we are coming towards the end of our first round of 16 projects, and we will be reporting on those through the middle of this year, and encourage everyone, partners being engaged through our internal processes, but also those outside the CRC, we'll be reporting on those on our website. So I encourage you to go there to find out more. And we've approved and are sort of proceeding with a further 8 new projects with a significant pipeline developing too. So that's all driven by our partners. And I want to recognise all our partners, of which Swinburne, where Jeff is from, is one. And these are driven by our industry-led research advisory committees. Today's topic, though, decarbonisation of Australian steel, is a significant priority area for HILT. We're really pleased to have Professor Jeff Brooks to deliver the webinar on this topic. Before I introduce Jeff, though, just a quick housekeeping measure. At the end, we do have about 15 minutes for Q&A. We won't be using the hands up. I noticed a few people have already found the chat function. Please jump in there, type your question in, and I'll be picking up questions, from that chat function. If we don't get to everything, Jeff has kindly offered to receive those questions after the webinar as well. So please, even if it's starting to look like a full agenda, please jump in there and raise your questions. So I'm going to introduce Jeff now. Jeff is a professor in the School of Engineering at the Swinburne University of Technology, and he's been researching the fundamentals of iron and steel production since 1994. Having held academic positions at the University of Wollongong, McMaster University, and since 2006, he's been at Swinburne University of Technology. Across that time, as you can probably imagine, he's worked with many, many steel companies, and he's published over 250 papers in this field and won numerous awards. I like this. In his spare time, Jeff enjoys competitive hockey, and I can vouch that he also organises an excellent office tipping competition. Very organised man. So without any further from me, Jeff, over to you. And like I said, I encourage everyone to put your questions into the chat function as we're going along. And I'll see you all back here in about 40 minutes. Over to you, Jeff. Thanks.
Thank you very much. Thank you for the nice introduction, Felicity. So today I am taking on a pretty challenging topic. I think about this topic a great deal, and I suppose discuss it with many of the major players involved as well. So what I'm going to try and do is explain it at the level where if you don't know all the details of the steel industry, it'll still make sense to you. There is some detailed information there, but a lot of it is just looking at the broad issue about what's happening with Australian steel. The first thing I'd like to say, it's a very exciting time. So it's not a boring time. There is so much drive for innovation at the steel industry at the moment. It's a great time to be a researcher. But it's also a time of a bit of anxiety about exactly what's going to happen. So I'm going to talk through some of those anxieties as well. So I'm taking some recent headlines from the media that have been coming out lately and just to get started. And this is one I saw on the BBC just a couple of weeks ago. And it said there's a race to build green steel plants. And it went on the example of what's going on in Sweden, where there are two companies committing to greenfield constructions of new plants that are based around hydrogen. And as you'll see, there's some very specific conditions about Sweden that actually make it a little bit different from some of the situation in other parts of the world. In particular, the availability of quite rich ores, which is an important issue as I will describe. So that's certainly quite interesting. So there's these new green steel plants. But then you see another story which came out a couple of weeks before that, which is about the Port Talbot Steelworks in South Wales. Now, I've been to this plant a lot and I've lectured there and I've done a little bit of research with the people at Port Talbot. And this steel plant is an older steel plant. It's got, I'd say, fairly standard steelmaking technology that we're about to discuss. And basically, the government wants them to go green. But the government's offering to put up initially £300 million, and then looks like it's shifting to 600 million. But the management of the plant say it's going to cost £3 billion, and I repeat that number because it's an extraordinary number, £3 billion to be going green. And there's obviously massive conversation going on about what's the future of the Port Talbot Steelworks. So in Sweden, we've got people building new greenfield sites. And in Wales, we've got people worried about an older plant surviving and who's going to pay the costs and how they're going to move to some sort of green steel future. Another very exciting announcement, which just came before Christmas. You might have missed it because you were getting ready for Christmas. But Fortescue Metals announced that they're getting together with Prime Metals and voestalpine, which are quite famous technology companies in the steel industry, to develop a fluidized bed process to make iron from Pilbara ores, the ores at Fortescue Metals mines, and hydrogen. And they're going to be building a pilot plant in Austria. And the intention of this pilot plant is to establish whether this is a good technology for processing the ores in Western Australia. So I'm sure every iron ore producer in Australia read that story with great interest. I certainly did. And it's a very interesting and exciting investment. We're all going to be watching that with some interest. And then this one is very recent. This is literally 2 weeks ago. And this is a sort of disagreement, or at least some sort of robust discussion going on between BlueScope and the government, which made the media. And essentially what's going on there is that BlueScope is planning to reline its blast furnace, which is technology based on coal and coke. And the government is trying to ramp up the rate of cutting of emissions from large emitters like BlueScope by 4.9% each year until 2030. And basically, the managing director of BlueScope said, well, this was actually threatening the viability of steelmaking in Australia. So they're fairly, serious words. And I'm going to not walk away from that. I don't enjoy political discussions. I'm more a scientist and engineer, but I'm going to talk to you a bit about where some of what are the issues there about continuing with blast furnaces or continuing with new technology, and some of the costs involved as well, which obviously is an important part of that debate. So I think, first of all, I'm going to go through a fair bit of technical detail, but I think I want to give a grand overview for a moment about what we're talking about here. So you hear the term green steel. When you actually look into the details, it's actually really about green iron making largely, because what happens is we've discovered over a long period of time that the best way to make steel is to first make an impurity from the iron ore, an impure form of iron, which is called iron, and from a blast furnace it's called pig iron, but that's a detail. And this impure material then goes into an operation where it's refined into steel. So essentially steel making is a two-step process. You make iron and then you make steel. Just as a point of comparison, aluminium is the other way around. What they do there is they get an impure ore and turn it into a pure oxide, and then they make it into metal once it's pure. So it's a different approach. But in steel, we do it this way, and there's good reasons why it's done that way. And at the moment, the basic formula used for about 90 to 95% of the world's iron is that you get iron oxide, iron ore, you put it together with some carbon, and you put it together with some fluxing materials, and you make a liquid iron, and you make a residue slag that contains a lot of impurities, and then you make a lot of CO2. All right, that's the basic formula that's going on around most of the world at the moment. The second most popular formula, which is more recent, is that you get that iron ore, which is iron oxide, and you combine it with natural gas. And that natural gas is basically turned into CO and hydrogen, and it makes iron, it makes some water vapor, and it makes some CO2. And that explains about 5 to 10% of the world's iron produced at the moment. Now, there's two other ways we could do it. The other way is that we could combine, get rid of all anything to do with carbon and just use hydrogen. So we then react the hydrogen with the iron oxide to make iron, and we make water vapor. And then the fourth way that we could do is get the iron oxide and put it together in an electrolysis process. So basically, basically dissolve it into an electrolyte, put some electrodes on it, and put some electrons in, and we'll make iron and oxygen. Now, the fourth way is not in a commercial scale at the moment. That's currently at a laboratory scale. When we're talking about green steel, what we're really talking about, there are many complications, but in essence, we're talking about going from those first two steps to those bottom two steps. We're talking about going from using carbon and natural gas to using hydrogen or electrons, all right? So basically, that's what people are really talking about when they say green steel. Now, this diagram here gives you a comparison between the conventional route and one of these proposed new routes. So what we're comparing here on one side, the left-hand side, is the blast furnace, and in the blast furnace we get some iron ore. We put it together with some coke. We make pallet or sinter. We put it into a blast furnace. We make iron. That's this impure form of iron, and then we refine it in steel making, and then we take it off and we make different shapes and different types of steels. What they're doing in hybrid, which is the process in Sweden, is that they're getting the iron ore and bringing it together with hydrogen that's been made from renewable energy. And from that, they then make an impure form of iron, which is called DRI. So it's a solid material, not like a liquid like from the blast furnace. And they then put an electric arc furnace, which is getting its energy from a green energy source. And then we make different shapes and sizes. So basically, what we're talking about is shifting from the left-hand side to the right-hand side. That's essentially what people are talking about. There are variations, but that's the essence of it, just to try and get that basic point across. Now, this has not been done in a vacuum of like, people, why are people doing this? Well, people are doing this because there's a general shift going on in our society towards renewable energy. And this is some people who've mapped out how they see renewable energy. And this is all about trying to affect climate change. So there's a big shift towards renewables, and there's a lot of debate in our country and all around the world about the pace of that and, how long it will take us to get there. But it's undeniable that there is a general shift towards renewables, and that is also then reflecting in heavy industry. So people are looking at not just energy generation, they're now looking at all aspects of industry about which generates CO2. And when you look at this, you find that concrete, steel, and aluminium, which are three extraordinarily important parts of our infrastructure in the world, they produce a significant proportion of CO2 that's been made, by humanity. So what are we going to do to lower that down? Actually, a lot of people think steel is the most obvious place to do it. There are ways of doing it in concrete and aluminium, but there are good arguments to say that steel is probably best placed to be able to really reduce CO2 significantly, which is part of what's driving what we're talking about today. People have done calculations, which are summarized in this diagram, which explains what that would really mean. And what you see on the left-hand side is the amount of CO2 currently produced. And then there is a projection of what steel production will be in 2050. And then they've done some calculations and they say, right, for us to be able to basically get to carbon neutral by 2050, we're going to have to reduce the CO2 from 1.8 tons of CO2 for steel down to about 0.2. So a 90% reduction. So what they're saying is, if we want to achieve the goals of net zero by 2050 and avoid large temperature rises on the face of the Earth, we're going to have to cut the CO2 from steel by 90%. Now, you might argue whether that number's right, but what we can all agree on, that's a very large change, all right? So this will not happen by incremental improvements. We will never achieve that by incremental improvements. We'll have to change our processes quite significantly. That's the major conclusion you reach from that. Now, at the same time, people have been proposing hydrogen as a route to not only make steel, but to generally be used in heavy industry. At the moment, hydrogen is dominated by production from hydrocarbons, and what we call blue hydrogen is where you capture the CO2, carbon capture technology, to make that hydrogen. What people are pushing for now very strongly is green hydrogen, which is where you generate the hydrogen from renewable energy, and your main products are basically hydrogen and oxygen. And there is a massive investment going on in Australia and around the world, because the current size of hydrogen electrolysis plants are really very small, but now there is investment in much larger plants. And according to these sort of estimates from the Institute of Energy, we can expect really massive growth in hydrogen production over the next few years. Now, these diagrams, I think, are a little bit optimistic. I think some of you would be aware that there actually is quite a lot of supply chain issues with building these electrolysis plants. But I think what is not debatable is that we can expect a lot more hydrogen to be available in the Western world and in Australia over the next 5 to 10 years. People are also hoping that this massive increase in hydrogen equipment and infrastructure will also see a reduction in costs, because simply put, at the moment, hydrogen is rather expensive. And people would like to see that as we mass produce the components of the electrolysis, that we'll see a big reduction in the capital and operating costs, or particularly the capital costs, sorry. And this is some projections there. And once again, these projections, I would suspect, have been rather knocked around by the supply chain issues that are partly connected to COVID and also the Ukraine war. But these are the kind of numbers that people are talking about. So what does this actually mean to the bottom line? Well, here is the diagram showing you about the cost competitiveness of green steel and green ammonia. So we're really interested in the green steel one, but when we look at the green steel, you can see there it's showing that with $2 to $3 per kilogram of hydrogen, you can expect a 50 to 60% increase in the cost of steel. That's a lot. Now, I actually think that number could be a little bit pessimistic. I've done my own calculations on that, and to me, that looks a little bit pessimistic. But you should know at the moment that a lot of hydrogen in the world is selling around about $4.50 US per kilo, all right? So for us to get the cost down, we need to really dramatically reduce the cost of green hydrogen. There are some people who believe that we can get under $2 and $1, and they think that that will happen, in the next few years, and that remains to be seen. I think the thing that is not beyond argument, or something, sorry, that is beyond argument, sorry, let's get that right, is that basically nobody believes that introducing hydrogen will make steel cheaper. all right? Everybody thinks it'll make steel more expensive. Now, that's a really important point because, say, for example, you're operating a steel plant in Australia, for example, and you go early with introducing hydrogen. So you do it like straight away, like right now. Then that means that you'll be producing steel that is more expensive than your direct competitors in Asia. So that's a really big issue. Now, in Europe, they're saying that they're going to protect their steel industry against that kind of issue. So they're pushing strongly for the introduction of hydrogen, but they're also offering to protect. So this is a very big political, social, economic issue in Australia. So the big picture is that, you know, steelmaking contributes a significant amount of the world's CO2. Some people say 7%, other people say as high as 11. I don't know which one's correct, but somewhere in that range. And there's this big shift towards decarbonisation, and there's also a general shift towards the concept of a circular economy, where we are living off what we are recycling rather than constantly making new things. So there's a big challenge about linking renewables to heavy industry, and people thinking that hydrogen, is the answer. It's one of the answers. And my question is, what are the major options for Australian steelmakers? So these are, now I gave you the simple picture before about, the chemistry, the overall chemistry, but here we have a more detailed diagram, and I'll just go through it quickly for those who aren't familiar with it. On the left-hand side is the blast furnace oxygen steelmaking route, which is roughly over 70% of the world's steel, all right? And it basically uses the blast furnace, it uses coke, it uses iron ore, and you then go through steelmaking. On the right-hand side is the next most popular way of making steel, which is using scrap and melting the scrap down by an electric arc furnace. When you look at the world's production, you'll notice down there I've also got the world's CO2. And the blast furnace BOF is a lot higher CO2 than the electric arc furnace. And that's because the electric arc furnace, you don't have to make the iron, you're just melting the steel. So it's not surprising. But it also means that there's a lot of reasons why melting scrap is very attractive in terms of decarbonisation, because you immediately have an advantage by just melting the scrap. On the next to scrap melting is direct reduction, or sometimes called DRI. And there are quite a few of these processes, which I'll talk about one or two of them in a minute. And this basically uses predominantly natural gas. Some of them use coal, and they reduce the iron ore down to a solid, and that solid DRI is then put into an electric arc furnace. And that's probably somewhere about 5 to 10% of the world's steel production at the moment. The smelting reduction, the one and the second one, I'm not going to talk much about today, but this is an attempt to get away from the blast furnace, but still produce a liquid iron that can go into the oxygen steelmaking process. And this process, there's been a number of developments, including in Australia, called high smelt. But at the moment, it's a very, very small part of the world's iron and steel production. But we'll talk a little bit about it. And I'm probably today going to be mainly talking about the direct reduction and the blast furnace, really. So Australia produces 5.5 million tonnes of steel. That amazes everybody in the steel world, given our tremendous resources. That's a very small number for a country with outstanding renewable energy resources, outstanding coal, outstanding natural gas, and outstanding ore. But that's what we produce. And we currently have 2 plants that are using the blast furnace, one of them in Port Kembla and then another one in Whyalla. One of the most important things about the Whyalla one is that it's right next door to a significant magnetite iron ore resource, which, as you'll see, is an important point. The 2 scrap melting plants have been designed, the Sydney one and the Melbourne one, have been designed around the scrap supply of the cities, Melbourne and Sydney. And so basically, when you have enough people producing scrap, you can justify economically building an electric arc furnace. I think it's inevitable that we'll have an electric arc furnace in and around Brisbane, or somewhere between the New South Wales coast and the Queensland area, because basically there's such a large population there, you think inevitably we'll be able to justify an electric arc furnace. So these are the 4 major plants. There is a couple of other specialty plants in Australia, but their production is quite minor compared to these 4 plants that I just described. We are maybe small in steel, but we're huge in iron ore. So we not only are one of the world's largest exporters, we're also one of the world's largest reserves. So this debate we're having is not just important to our producers, it's all our steel producers, it's also important to the people who are exporting iron ore. So what Australia does in this area is of great interest around the world. One thing to realize about ore is that basically ore grade around the world is going down. So essentially, years ago, you could find ores above 65, 66, 67% iron, which are very rich ores. But now in Australia, for example, a lot of our ores are more between the 62 down to 58, 57 area in iron. And this is going to have a big impact on these different choices. So we're trying to bring hydrogen in at the same time that we are having declining ore grades, which is an important point. The ores in Australia that we mainly export at the moment are mixtures of hematite and goethite. This is particularly in the Pilbara. But magnetite ores are also becoming important. Historically, magnetite ores have been a little bit expensive to process. But one of the things about magnetite ores that are very attractive is that their magnetic quality of Fe3O4, that's why it's called magnetite, means that you can upgrade it using magnetic separation. So you can get much richer ores if you in fact have a lean ore. All the gangue minerals that are inside these ores add significantly to the cost of making iron and steel. So basically, a high gangue means extra cost, as you will see as we discuss it. This is a nice little diagram showing you the impact of having putting a DRI into an EAF, replacing scrap. So basically, because the DRI has quite a lot of gangue in it, you will get an increase in the amount of energy as you have to use, as you can see on this line sloping upwards, right? So the line goes upwards because basically you're having to melt all this gangue. Now, this graph has been constructed for rich ores, right? Because at the moment, most of the DRI going into electric arc furnaces are from rich ores. But what we're expecting in the future, if this becomes an important route, is the slope of that line will go up dramatically. And that has big repercussions about the viability of using an electric arc furnace when you've got not such rich ores making your iron. We won't talk much about scrap today, but just something to realise about scrap is we don't have enough scrap in the world to be able to supply our world steel. And a lot of the scrap that is coming into the world is obsolete scrap, which has got a lot of residues in it and a lot of troublesome impurities. And it's actually very difficult to make high quality steel. So it's unlikely we can answer our issues with steel just relying on scrap. We would really need a revolution in our scrap sorting technology. So basically, ores are drifting downwards. The DRI is currently made from high-grade ores. That's what we currently do. And it's not really clear exactly what the expanded DRI production, which is what we're expecting to happen with hydrogen, how that will play out. Scrap quality is a major obstacle and something that is, an ongoing issue. And green hydrogen, as we've already discussed, is currently costly, and we're hoping that it will go down in cost, but that still has to emerge. So what are the major choices? Well, I'm going to talk through each of these. One of them is, the first obvious one is electric arc furnaces, just to switch to green energy. So if we switch straight away to green energy on our Sydney and Melbourne plants, we will have a significant impact on the carbon footprint of those plants. So that's an obvious thing to do, and I believe will happen. The other one is for our blast furnace BOF operators to see the switch to a DRI EAF route, or to try find a way of bringing more hydrogen into their blast furnace and more scrap into their BOF. Actually, currently at Port Kembla, BlueScope is doing a lot of work to get more scrap into their BOF, and actually I think they're quite innovative in that area at the moment, and they are actually, that is a net benefit because you are basically meaning you don't need to produce as much iron, which therefore means you don't need to make so much CO2. So that's quite interesting development at the moment. And the other one is, of course, to switch to a different sort of furnace where you basically have a furnace designed to remove all the gangue. That's another option people are looking at. And yet another option is the one I mentioned before, which is electrolytic processes, which I'll briefly talk about. So basically at the moment, there's been a whole lot of work at trying to see how much hydrogen you can get into a blast furnace. So there's been work going on in Japan and Europe. Thix and Krupp have been doing work bringing hydrogen into the TWEAR line. So that's the bit down here at the bottom where my arrow's pointing here, number 6. So they're trying to bring hydrogen in there to replace carbon or coke coming in from the top, basically. And in Japan, they've been doing a lot of work over the last decade to try and find cheap forms of hydrogen from various syngases to replace the carbon coming in. And they've also done work on trying to get clever with the heat distribution in the blast furnace. And they're aiming at trying to get a 30% CO2 reduction, which is quite large, but still probably a long way short of what's required for to achieve the goals of 2050. Just a little bit about the blast furnace. With the blast furnace, the carbon that comes in the form of coke, which is shown in these dark lines here, it serves many purposes. The first thing it does is it provides a physical structure inside the furnace to distribute the gases. So the coke is actually providing an important structural role inside the furnace, but it's also ensuring that you have enough heat down near the bottom here so you can melt the metal and slag and collect the metal and slag at the bottom. One of the concerns of bringing hydrogen in at number 6 through the TWEAR line is that the reactions involving hydrogen are endothermic. That is that they take heat in, not put heat out. So what that means is there is a risk of making the furnace too cool in this area and near the TWEAR area. And in fact, there's been a lot of calculations and some measurements done on that. And this is a real concern about trying to operate a blast furnace with a lot of hydrogen. As it stands at the moment, people are saying that they can basically expect somewhere between 80 to 30% reduction in CO2. So it's not clear whether you can go above 30% using hydrogen injected through the TWEARs. Some people think you can displace up between 14 to 32 kilograms of coke from the input per ton of hot metal. So this is an area that is still undergoing research, but at the moment there's a little bit of pessimism that we can push much beyond 30%. So that's an area which I think it's still got room for innovation. So I would say don't write off the blast furnace yet, but watch this space because I think there is still space to innovate there. But at the moment, it doesn't look like we can get as much hydrogen into a blast furnace as is required to meet our goals. Now, the other people who are been developing iron-making processes are Midrex. They're one of the DRI producers, and they've been running their DRI processes now for 30, 40 years. And these are quite commercial, successful units. And they bring in natural gas, and the natural gas is turned into CO and hydrogen. It then goes into a shaft, and then the gases go back and are recycled around a reformer route. And this then produces a solid product, which is then shipped or put directly into a furnace. And there are another famous variation of this is called the HILT process. And these are very well established processes. Something you should know about these processes is that they already operate with quite high hydrogen. So if you looked at the incoming hydrogen gas going into this furnace, it could be as high as 90% in the existing processes. So that's something important to keep in mind. This is showing you the growth of these processes. So basically the two most prominent ones are Midrex and HILT, and they take up a large proportion of the world's DRI production using this approach. The Swedish initiative Hybrid is basically using a HILT furnace and replacing it with 100% hydrogen, and then putting it into an electric arc furnace which got supply from a green energy source. Now, just remember, a very important thing to remember is they're using very rich iron ore. So that's one of the reasons why this route looks viable in the Swedish context, is because of the availability of rich ores. One of the interesting aspects of it is that the hydrogen that they use is stored in caves. They store the hydrogen in salt caves near the plant. This is at the moment a very small scale plant. It's really barely at the pilot plant scale, but they're hoping to build this into a much larger plant as laid out in this diagram here. So these shaft DRI processes have been already proven at commercial scale with high hydrogen content, and they basically are pretty close to full commercialization with 100% hydrogen. So there's a number of large-scale investments going on at the moment in exactly doing that. And I know of several European steelmakers who plan to install a hydrogen shaft DRI process before 2030. So that's what they're doing. And what you need to keep in mind is that this has largely been developed for high-grade ores. And there's actually limited public data, at least anyway, on how they operate with low-grade ores. I am aware that Midrex, I know Midrex has, and probably HYL as well, have operated with lower grade ores, but there's not a lot of data about exactly how they perform. One thing important to realise about these processes is that palletization is required. Now, the other approach is using fluidized beds, and this is a process called Circaret. And this has a two-stage fluidized bed process. And this has actually been done at commercial scale. This has actually been operated at full commercial scale some 15, 20 years ago in the West Indies. And they basically were produced iron with hydrogen and then shipped it to steelmaking plants around America. So we've already actually done at commercial scale hydrogen iron making and EAF steelmaking. And they are now selling another version of this process to anybody who's interested. Prime Metals have developed this is what our friends at Fortescue Metals have invested in or are investing in. And they have got a staged fluidized bed process, which uses hydrogen. And this has been tested at a pilot plant scale in Austria. And it's building on some other technology in fluidized beds that Prime Metals and POSCO and other companies have been involved in. And this process is the type of thing that we're going to be seeing built at pilot plant, so demonstration level, with help with FMG for West Australian ore. So this will be fascinating to see how this performs. These fluidized bed processes, they're building on existing fluidized bed technologies. Some of the issues with fluidized beds are sticking of ores. So ores tend to stick when they get hot, and that's not helpful to a fluidized bed. There has been some recent work that shows that if you control the temperature very carefully, you can avoid that problem. But that's going to be one of the big issues that they will be testing in this joint venture between Fortescue Metals and Prime Metals and voestalpine. The other thing also is how many stages do you need? You know, obviously the number of stages will affect the level of metallization of the product, but it'll also affect the capital cost. One of the most attractive aspects of this of these processes is you don't need palletization. In Australia, there's an exciting development going on. It's not a fluidized bed and it's not a shaft. It's basically what we'd call a flash smelting process, and it's been developed by Calix. And I should reveal that I'm quite heavily involved with this, so I'm not a completely objective observer. But they've built this pilot plant in Bacchus Marsh, and it's based on using electrical heating and using hydrogen only as the reductant. So basically trying to minimize the cost of using hydrogen. And they basically drop iron ore fines down a shaft and react it with hydrogen, and they make a DRI. And they're currently testing this pilot plant, with a range of different ores. And as I said, myself and Swinburne University are heavily involved with that. So the big picture is that, I've already gone through that, excuse me, that's a repeat. Now, let's get down to this business of what to do with these high-gang ores, which I've been promising to talk about. So high-gang ores, that is more a problem, for example, that would exist for BlueScope, because our friends in Whyalla are near a magnetite deposit, which they can realistically expect to upgrade. The people in BlueScope, they are trading on ores around the country. They probably buy a lot of ores from the Pilbara, I'd be guessing. I don't know exactly. And so they're contemplating an intermediate process where you melt the iron, the DRI, to get rid of the slag. Some people call this a melter. Some people call it a smelter. There's a variety of names, but I'll just give you an idea what it looks like. So this is a recent presentation from M&S, where they're planning to install these furnaces in steel plants. And basically what it is, you'd have like a shaft process, like a Midrex or HYL, and its product would go into these big arc furnaces, rectangular arc furnaces, and these would produce iron, which then go off to steelmaking. So what they're really doing is replacing the blast furnace with two furnaces, because basically the shaft is really the top part of the blast furnace, and these electrical heated furnaces here are really replacing the melting. So basically this is a blast furnace split into two. That's really what it is. And the energy for the melting is coming from electricity. These furnaces already exist. A number of these furnaces already exist in the world. And this diagram is showing what scale they're up to. And basically the scale they've been building to is still some way short what you'd probably want from a steel plant. So there's a whole lot of development to go there to try to get these melting furnaces or smelting furnaces, depending how you see it, up to the scale that people are interested in. Now, when people do calculations about how much CO2 you could reduce, they basically show that these processes can dramatically reduce the CO2 compared to the blast furnace. They've looked here at the options with carbon capture, without carbon capture. Now, carbon capture is a whole big topic in itself, but basically these melting furnaces can achieve the kind of drops in CO2 that people are looking for, particularly by 2030 or 2040. This is a diagram that's most interesting. It was produced by Prime Metals, and what it's showing is something that's very important to Australia. And I'm actually, at the moment, reconstructing a version of this diagram for the Australian situation through the HILT CRC. And what this is looking at is the cost it takes to process an ore compared for the grade of iron. So a lot of Australian iron ores are at this left-hand side of the diagram. And in Sweden, they've got ores at the right-hand side of the diagram. And what it's showing is that this smelter or melter, depending what you call it, it is the cheaper option at low-grade ores compared to the electric arc furnace. So basically this diagram is saying if you have a lean ore, you probably want to have a smelter with a BOF, and you probably want to have, for a high-grade ore, you probably want an EAF, all right? So this is, a generic diagram. And as I said, I'm trying to understand this for Australian conditions through a project that's funded through the HILT CRC. So here's a few questions for iron ore producers to consider. How does the cost of extra mineral processing versus the melting smelting of DRI, how do those costs compare? Should we put our money into extra mineral processing, or should we put our money into building a melter? That's a dilemma that I'm sure that our friends at BlueScope and InfraBuild and Liberty are thinking through, as are the iron ore producers. Can we convert the hematite goethite into magnetite, so make it magnetic, and then use magnetic separation to make the ore rich? Is that a viable idea? Hydrometallurgical treatment of ores, that's another idea I've heard people talking forward. Should we just be expanding the processing of our magnetite ores? This is a topic of a whole separate talk, this particular slide, but just to give you some of the issues that are being discussed at the moment. Molten oxide electrolysis, which I've run out of time to talk about in any depth, is a very low TRL technology at the moment. It's basically, the concept is that we get the iron ore into an electrolyte, we apply an anode and a cathode, and we produce metal as per the aluminium process. It's a basic idea. There's only been really limited development of the anode materials, because very quickly you realise for this to work, you need to have an anode, a successful anode. And there has been done some very nice work at MIT, and this work continues, but at the moment, it's still very early days. And one of the next step that is being produced here in America is Boston Metals, is that they're currently looking to build a demonstration plant in 24-25. There are lots of questions about productivity and capital, and lots of questions about anode materials. One of my PhD students, Matthew Humbert, he gave a talk at the recent conference in Newcastle, and he went through all those issues in some detail, which I can't do now. And I'm sure he can provide his slides if you ask him politely. But it is a big issue, both the anode materials, the productivity and capital. So watch this space. This is a technology that's developing. So what are the decarbonisation options for Australian steel? It's taken me a long time to get to this slide. So the first obvious thing is providing green electricity to our scrap melting plants. That's the first simple, obvious step that we should do. I don't think that's a no-brainer that is something that we should do. I think we will be considering, and I mean us, I'm not going to tell BlueScope how to do their business, but I'm sure BlueScope are considering some sort of hydrogen DRI melter process at Port Kembla to deal with a wide range of ores. In fact, I know they're thinking about that, but they tell us, but it's obvious that they should. The other one is to, in Whyalla, since they have access to a magnetite, they can probably use a hydrogen DRI to an EAF to replace the blast furnace, all right? So what I'm expecting to happen is that the blast furnace will eventually be replaced in Port Kembla with some sort of DRI melting system, and I'm expecting in Whyalla that it'll be replaced by a hydrogen DRI with an EAF. We could also create an export industry in West Australia based on making iron, using these processes. Dave Trotter recently gave a talk in this same webinar series about that, and I think that's an open topic. And the other thing I'd like to say is, well, the electrolysis processes are a long way from commercial reality. Why can't Australia not develop this? Why are we waiting for people overseas to do this? I think we could do it quite easily. Now I've got some broader issues that I would like to raise. These are sort of in the political economic sphere. So the first issue is I ask is who's going to make the investment to make these plants be converted into green? How much of it is going to be private money? How much of it is going to be public money, or at least public support? I think that's a very big question, and that's at the heart of, I think, the recent debate between BlueScope and the government. And do we need to protect our steel industry in this transition? So if we know that hydrogen steel making is currently more expensive, and we could expect it to be quite a bit more expensive, how are they going to survive? How are we going to do that? So I think this needs to be a mature debate about that issue. I haven't talked about carbon capture, storage and utilisation. I think it's a really interesting question because it's another option, right? And it's an economic question and it's a political question. So where would it be economic, right? Which part of Australia would it be economic? But also, is it got any political viability? Is it ever really going to get up? It seems to be that carbon capture technology has not been politically popular in the Western world. So I do wonder whether you can get both political and economic agreement there. And I would like to say, why can't we be technological leaders in these areas? I think we are with what FMG is doing with Vilstaalpont. I think that is some sort of technological leadership. I think what BlueScope is doing by pushing a lot more scrap into the BOF is some sort of technological leadership, so good on them. And I think Calix is an exciting company as well. But I think in general, we should be thinking about how we can be leaders in this and not just followers. At least we should be discussing it. All right, Felicity, I think I've overstayed my welcome, and I hope I haven't confused anybody.
Thanks, Jeff. And if you can pull down your slides, and I'll get Louise, please, to bring Tom Honeyans and Gus Nathan. Tom is doing some of the research within HILT CRC that Jeff has sort of spoken to, and as well as some additional areas. Gus Nathan is HILT's research director. While they're being brought up, there are a lot of questions, and as I said, we will share those with Jeff. We're not going to get to them today. But one that maybe you haven't touched on that's perhaps a broader topic is wood switching from the blast furnace to an EAF. And perhaps this is a broader question on many of the technologies. How do they affect the properties of the steel that's being made? And is there any barriers in that regard?
That's a good question, and I would say in general no, but the BOF has got a lot of nice features about it in terms of quality of steel. So that's one of the reasons why the Europeans are going for this melting technology between the DRI, because it's not just the fact that they can get rid of the gang, but it's also because the BOF is a very nice way to make steel. Now, you can make good quality steel in an EAF, but I think in a general sense, it's a bit easier to make in the BOF. So I would say there are quality issues there. They're not insurmountable, but there are issues there if you go totally to EAF.
Thanks, Jeff. And Tom, I'll pass over to you. Thanks.
Thanks, Felicity. And yeah, Jeff, I think you mentioned it a bit earlier and probably didn't want to go into detail because of the mixed audience. But yeah, the scrap and over time, scrap will have these residual elements build up, won't it? So there is potentially difficulties around that where can make good steel out of an EAF, and they do that very successfully in the US. But they have very good control over their scrap recycling and how they control the residuals in the scrap, and then they do end up having to add some direct reduced iron to help with that quality.
Correct. Yeah. You're going to ask me a question, Tom?
Oh, I think I've just been asked to comment, Jeff. But
sorry, I thought it was a question. No, I totally agree with what you just said.
But I can if you like. What about phosphorus? Yes. So what if with the high phosphorus load that we're going to be putting into these processes, do you see advantages?
Tom, Tom, that was a bit of a Dorothy Dixon because I've done a lot of work on phosphorus in DRI. So phosphorus in DRI, it will create problems in the process. It'll essentially mean you'll need more fluxes. You'll probably have longer processing times, but I don't think it's a showstopper. I don't think it's a showstopper to any of these new routes, but it's certainly an issue. That's how I would see it.
Thanks, Jeff. And Gus, you've got a question for Jeff.
Yes, thanks, Jeff. It was a great presentation. I'm just wondering if you could comment a bit more on more the global supply chain issues that Australia, or opportunities that Australia is fitting into, because obviously what we're looking at potentially doing is exporting, a mix of potential green ferrous feed material, and there are different opportunities in different regions. You mentioned obviously Western Australia, but there's also other regions with magnetite resources. And where do you see like some of the transitions in, for example, maybe going to a beneficiated component only, or going through to DRI, and which kind of routes? Maybe you can just talk about that opportunity a bit more. Thanks, Jeff.
Yeah, that's a really complex topic in itself. And just what's going on there is that basically everybody in the world is watching Europe, right? And they're watching what the Europeans are doing. And if that technology takes off, and it's these different hydrogen ion steelmaking routes, and everybody starts following suit, what will happen then is that there will be a demand for higher grade ore products from Australia, right? So at the moment, our current business model may have to change. And it may change either by we do a lot more mineral processing and get a lot cleverer in trying to upgrade the ores, or alternatively, people start wondering whether we should make the iron itself as a product, right? We're not there yet because basically, Europe is a relatively small part of the world's steel chain, right? So even though the Europeans are doing these exciting things, what it will really matter is when we start seeing the Chinese, the Japanese, the Asian steelmakers pushing us for that. And that's not happening yet. So I noticed that David, when he gave his talk about iron ore producers, and he basically said, well, we can keep selling ores. That was one of his messages. And he's right. But somewhere along the way, I don't know exactly when, I'm not Nostradamus, there'll be pressure, though, for us to start upgrading. And I think that's why companies are investing in research to understand how that would work. But what's really hard, Gus, to say of any confidence about when that will start taking off. I think it's some years away, but it's not decades away. That's my thought. Anyway, my guess.
Thanks, Jeff. I'm going to ask one last question because we are only a couple of minutes from wrapping up. I'm going to thank Nick for this great final question. Is the future in Australia green steel, or is it green iron? Comment.
We basically, as a society, need steel. We are an advanced technology country. We'll make steel. I don't believe Australia will let its steel industry, wither. So what's going to happen is we're going to have to change. We're going to have to change our steel. So we're going to have green steel for sure. I'm sure of it. It's just when. I think the issue about the green iron is, is harder to predict exactly how that's going to play out. But I do believe that we will find ourselves making higher grade iron ore products in Western Australia, and other parts of Australia. And the exact timing of that will depend how quickly the rest of the world takes up these technologies, which is hard to predict. But I think the 2020s are exciting for metallurgists. The 2030s may be unbelievably exciting. That's what I think might be happening. I feel like the 2030s might be where everything sort of really happens. But we'll hopefully be watching and seeing what goes on. That's my prediction for the city.
A great wrap up, Jeff. Thank you. And thanks to everyone for joining us today. There's been some questions. We have recorded this and that'll be available, and we will make the slides available. So thank you once again, Jeff. Thank you to everyone who contributed in the chat. We've got a wealth of knowledge within this network. I see a lot of the questions have been answered by others in the webinar. So thank you for the interaction today. It's we'll put them to you as well, Jeff. And look forward to seeing you all soon. Thank you.
Bye.